welcome grade 12s, and today what we're going to do is we're going to continue with our talk about work, energy and power. Last week we looked at just work and energy, a little bit of work energy theorem. This week we're going to add in mechanical energy, I can hear the groans, and a little bit of power, and we're going to go from there, okay? So the first thing we need to deal with, of course, is the important terminology. So we're going to look at some words we didn't look at last week. So I'm going to give you 2 minutes in a second, and you're going to quickly discuss what you understand about what a conservative force is, what a non-conservative force is, what the principle of conservation of mechanical energy is, and what power is. Okay, so those are very important terms. You're going to see them lots. So I'm going to give you 2 minutes. Okay, are you ready? You've got your pens and your pencils and you're ready to do discussion. Great. So your 2 minutes starts now. All right, grade 12s, how did you do? I know 2 minutes isn't enough, but at least I'm hoping you got some sort of conversation going. So we're going to talk about those. So as we go through the notes today and as we go through some questions, make sure you listening out for those terms, okay? Now, last week, I showed you this mind map, and it's a great one because we're just going to quickly remind you of some of the stuff we did. So last week we did work, and we said W equals F delta X cos theta. Remember that that had to do with the force and the angle of the force to the direction of motion. Then, of course, we looked at the work energy theorem. Work energy theorem here, we didn't really consider if there was friction, but we said that we can only have the work energy theorem when W net equals change in kinetic energy. So now what we're actually going to do here is we're going to look at these and we're going to go, now we're going to actually consider energy and the law of conservation of energy, because that's quite important, okay, and whether we're looking at normal, just energy as a whole, or whether we're going to be looking at mechanical energy. And then we're going to talk about non-conservative work, which of course is done by a non-conservative force, and we need to discuss what that is. And of course, what's really, really important over here is we need to do the whole thing of mechanical energy, which is potential and kinetic, remind you what those are. And then lastly, what we're going to look at is power, because power is related to work, and power relates to how much work we can do per unit time. I'm hoping you've seen that before, and of course we all talk about how powerful a car is, or an engine, or a hairdryer, and in fact our electricity we pay for in terms of the power that the electricity uses, which is the amount of work that's done per unit time. Okay, so now we're going to go through those. So let's start with the important concepts, and the first thing is, what is a conservative force? Now, conservative forces, the definition of a conservative force A conservative force is a force for which the work done in moving an object between 2 points is independent of the path taken. That's a very definition. And what that definition is saying to us is that a conservative force actually means that mechanical energy is conserved, okay? And our examples of conservative forces are things like gravity. Gravity is a conservative force, even though when I'm doing work against gravity or gravity does negative work, all we're doing is we're changing kinetic energy into potential or potential energy into kinetic, okay? So that's an interconversion between mechanical and kinetic, potential and kinetic, sorry. Both of those are mechanical energies. And when we look at gravity, for example, whether an object drops straight down or whether it goes down a slope, we actually don't care, because what we're looking at is the vertical height. That's the part that's important, which is why we say it's independent of the path taken. It doesn't matter, okay? A non-conservative force, okay, here is a force for which work is done in moving an object between 2 points, and it depends on the path taken. Now, where this is important is friction, okay? So friction, for example, if we're looking at, say, a roller coaster, which you've seen before, when I consider the gravitational force on it, I don't care how the roller coaster moves. However, the friction on this roller coaster, or whatever path it is, whether my object's here at the top or whether it's here at the bottom, the friction's going to change. Because of the angle of the slope, the friction depends on, and we actually need to know the whole distance that it goes on. So it absolutely depends on the path, whether it's a 3 meter long path, whether it's 2 meters, whether it's 1, whether it's 10. Okay, it makes a big, big difference. Plus, with friction, so friction is a non-conservative force, always. Okay, friction, air resistance, any of those things. What you need to remember here is that these forces take mechanical energy out of the system. So it changes mechanical energy from kinetic or potential, and it becomes sound or heat. Okay, you can even think of it, especially now winter's coming. So when you rub your hands together, we have friction happening. And why do we do that? Because now the kinetic energy of our hands creates heat between our hands. Okay, so kinetic energy changes to heat energy. Energy is being conserved, but not mechanical, okay? So conservative forces, doesn't matter about the path. Gravity is a conservative force. Non-conservative force does matter about the path because we're taking mechanical energy out of the system. Very, very important, okay? So let's remind ourselves of our conservation of energy principle, which you've known since grade 8, which says to us that energy, the total energy of a system, cannot be created or destroyed. It is only transferred. There is no exception to this, okay? Doesn't matter what the form of the energy is. It can change form, go from heat to light to sound to potential gravitation to electrical potential to chemical potential to kinetic energy, rotational energy, all sorts of things, okay? Energy is always conserved. In work, we're concerned about mechanical energy. That means we're only concerned about potential and kinetic. Now, we're going to add a little bit of an equation here, and this is where you've got to be careful. And your subscripts become very important. WNC. NC stands for non-conservative. So in other words, okay? In other words, the work done by friction, the work done by air resistance, the work done by the force that changes our kinetic energy into sound or heat or light, okay, is now equal to the change in kinetic and the change in mechanical potential, because this is mechanical energy. So basically, the work done by my non-conservative force is the change in the mechanical energy of my system. So if I drop a ball from a height, it has a certain amount of mechanical energy as potential and kinetic because of its height. As it drops, if I ignore air resistance, then the mechanical remains constant. If I don't ignore air resistance, then I'm going to get a certain amount of heat. Okay, that heat's got to come from somewhere. That energy's got to come from somewhere, and that's the transfer of potential. Okay, so it's how the potential changes. So we remember that kinetic energy, EK is kinetic, it's movement energy, so half mv squared, m being mass, v being velocity, EP, potential energy, okay, and G, don't forget, is 9.8 meters per second squared. I'm writing nice and straight today, it's great. H is height measured in meters. You've done these equations often. Now, this section, now we've said we've done the principle of conservation of energy, which says energy cannot be destroyed, created or destroyed, it's simply transferred. When we're looking at the conservation of mechanical energy, the total mechanical energy, the sum of gravitational and kinetic energy in an isolated system remains constant. Isolated system means net force is zero. Okay, net force is zero. That is really, really important. If there's friction, it's not an isolated system. Okay, we need to be very, very careful with those. All right, and it means that our mechanical energy can't be conserved. Very, very important. Okay, so what we're going to do is I want to start looking at a question. We're going to take a bit of a break before I let you try it, but I want to just talk about the way we get these questions. So if we look at the question that we're going to do, okay, it says to us, John applies a force of F to help his friend in a wheelchair to move up a ramp of length 10 meters and a vertical height of 1.5. Now, guys, please don't get worried about the fact that you've got a length and a vertical height. You may need to use a little bit of trig in this section because, of course, this is a right-angled triangle. Okay, so this angle may become important later on. We don't know yet. We're not going to have our moment just yet. But this height means that probably somewhere along the way I'm going to need to use potential energy. Okay, so we're going to keep that in the back of our minds. Then they say that, so we go length of 10, it goes up. The combined mass of his friend in the wheelchair is 120 kilograms, so we know what that mass is. The frictional force between the wheels and the wheelchair, the surface of the ramp, is 50 newtons. So now remember, he's being pushed up the ramp, friction must act down, and that's 50 newtons, okay? So that's friction. The rotational effects of the wheels of the wheelchair may be ignored. Guys, they just put it in a statement like that because sometimes we tend to overthink the questions and we go, oh, but what about, and we try and make it into a real world situation, which is great. And I love that thinking because we're going, there's more to consider. However, we're at school and we want to try and make it simpler because we also don't want to make the maths that difficult, okay? As soon as we put rotational effects in, then we've got to add all angles in on radians and we might as well just, yeah, it gets horrible. So we don't want to do that, okay? So don't stress about it. It just means we can ignore it and all we're going to look at is if it was a box being pushed up, for example. Then, very important statement right now, it says to us, the wheelchair moves up the ramp at constant velocity. That is very, very, very important, okay? But before I explain to you why that's very important, we're going to take a break. And during the break, I want you to think about why I'm telling you that that statement is so important. I want you to think about what that implies for us because that gives us a very, very, very important hint on how to answer these questions, okay? So that's incredibly important. I think you're getting that. I've said that lots. So we're going to take a short break and then we're going to carry on with this question, okay? So you've got something to think about and I'll see you in a little bit. Welcome back, grade 12. So, you had to think about what constant velocity means, okay? And I'm hoping some of you came up with it and you went, I know constant velocity means acceleration equals 0. That means, Newton's second law, that if acceleration equals 0, F net equals 0. Very, very, very important. So, we've now gone through the question. We've got quite a bit of information written on our diagram, which is going to make life easier. So that means, you can all hear it, it's time for you to try some questions, okay? So we're going to use non-conservative force. We've got our diagram, so I'm going to put a couple of questions up. I'm going to give you 3 minutes. There's 3 questions. You're going to get through as many as you can. I'm giving you 3 minutes, grade 12s. Okay, so you got the diagram. I'm now going to give you 3 minutes, and we're going to go from there. So you ready? Okay, your 3 minutes start now. So, grade 12s, I'm hoping question 1.1 and 1.2 went really quickly and that you've been working on 1.3 actually, because really I gave you the answer to 1.1 and 1.2 as we went along. So, if we look back at our diagram, okay, so remember, the first question was, what is the magnitude of the net force? Now, we actually answered that because earlier I said to you that, of course, we have that constant velocity. That's really important when you answer this next question because they say, what is the magnitude of the net force? Well, F net has to be 0 newtons. Your reason being that acceleration equals 0 because velocity is constant. That should be a C. constant. All right. Now, because velocity is constant, if you look at F net equals ma, if a is 0, F net is 0. Nice and easy. Okay, so we've got that one down. Perfect. Now, we carrying on to 1.2. Now it says to you, what is the magnitude of the net work done on the wheelchair on reaching the top of the ramp? Well, if we go and we look through this, I'm going to do the explanation before I do the answer. Remember, W net, besides being, well, there's two ways we can look at it. W net is change in kinetic energy. Velocity is constant. That means the kinetic energy won't change. If kinetic energy doesn't change, then the changing kinetic energy is 0. So that would mean that W net is 0 joules. Or you can look at it from the point of view that my net work is also equal to F net delta x cos theta. And if F net is 0, then W net has to be 0. Okay, so that actually helps us quite a lot. So, next question. Now this is where life gets quite interesting, because now they say to us, what is the work done on the wheelchair by force F? When we look at a question like that, grade 12s, our first thought is always to go to, can I use W equals F delta x cos theta? So we go back to our diagram and we say, well, I know theta is going to be 0 because it's in the same direction as motion. I know x, it's 10, but I don't have F. Okay, that's a problem for me. Then we look at this and we go, but there's a non-conservative force here. There's friction, okay? And here, this becomes, okay, so how does this help me with the friction? And then we've got to actually look at the next question, because it says, what is the magnitude of the force? So I need to work out what the, what am I saying? I need to work out what the work done by the force is first, then I can work out what the force is. Okay, so that's the way around we need to work at it. So we're going to go, okay, what do we know about the system? Well, what I know is that kinetic energy is constant, and I know that the potential energy changes. That means I'm going to need to use this. Okay, I'm going to need to use that. This non-conservative force here, that's actually a combination of both the friction and the applied force. They're both non-conservative, okay, because the applied force isn't really helping us here in terms of kinetic and potential. So when I go back here, we're going to go, fine, let's look at this, and we're going to go, okay, so what I know is that, so this is 1.3.1, okay, is the work done by my non-conservative force is going to be delta EK plus delta EP, okay, but we're going to have work done by the applied force, okay, plus work done by friction, which is going to be this. Now life gets interesting for us, because now we go, okay, I'm looking for the work done by the applied force, okay? So that's what I'm looking for. That's what I'm going to have to be able to work out. Okay, work done by friction means that I'm going to have to take the frictional force, delta x cos theta. Now we're going to use a little bit of our brains. We go, well, velocity remained constant. If velocity remained constant, then kinetic energy can't change because Vf minus Vi will give me naught. So delta Ek can be 0. Yeah, we like this. Okay, over here, we're going to have to go final height minus initial. Okay, fine. So, work done. My friction was 50. It goes 10 meters. Very important. Friction goes down the slope, the object's moving up the slope. The direction in which the object is moving, the wheelchair, and the direction of friction are opposite, which means theta is 180. Okay, and over here, my mass was 120. This was, G is always 9,8. My final height was 1,5 minus, always write too big for the screen, but it's all right. Now, initial height is 0 because it starts at the bottom of the ramp. Initial height 0. Nice and easy, not a problem. And you know what? Now, whoops, that's not what I wanted to do. Oh, I love these boards. Okay, now, oh, again, really doesn't like me today. All right, there we go. What we need to recognize here, now it's a maths problem. Now it's about being able to use our calculators. And I'm not going to do all the maths with you. Unfortunately, we're both strapped for time, which is very sad, but it's okay. But what I can tell you is we're going to get W applied here, and this is minus 500. Guys, please, 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 this is really important. Up until now, whenever you've dealt with something like friction, you've always put a negative in because friction is in the opposite direction. So we put the negative in as a force. But because I'm using cos 180, that accommodates that negative. You never, ever, 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 ever substitute a negative force into this. Okay, don't do it. You'll get into trouble. Okay, and 120 times 9,8 times 1,5 is 1,764. So the work done by my force is 2,264 joules. Yay! Done the first question. This helps us answer the next part because the next question said to us, what is the magnitude of the force? Well, that's easy enough because now, okay, so this is the next part. Let's do another color so we can see the difference. There we go. Now we remember that my applied force is F delta X cos theta. I know what my applied work is. We've just worked it out. Okay, we want F. It goes 10 meters. And now it's about what my theta is. Cos theta here, remember, my wheelchair is going up the slope. My applied force is going up the slope. That means it's the same angle, 0 degrees. Okay? And hopefully, we can all see what this is going to give me because this is going to give me 2,264, which will then equal to 10 times my force. Cos theta is 1. We like cos 0. Okay, so that means my force is 226,4 newtons. Okay, significantly bigger than friction. That's okay because we need to get him up the slope. Okay, very, very, very important. And of course, a lot of the energy that he's using has to be is the fact that he's got to overcome friction. Okay, that's quite important here. You guys all okay with that? Oh, I know we don't like this section, but that's okay. All right, I think it's time for a little break. Then we're going to deal with power, and this is a nice section. You'll like this one. This is a little bit easier. There's a couple of hints, but we'll be okay. So we're going to take a short break, and then we're going to do power. So I'll see you in a little bit. Welcome back, grade 12. So let's hit the last piece, and hopefully we'll get to do a little bit of revision in the middle. So now we're going to deal with the concept of power, and hopefully this is nothing new. Now, power, of course, is the rate at which work is done. So it's how quickly we do work or how not quickly we do work. It depends. Okay, so because it's the rate at which work is done, that means it's work divided by time. Okay, remember that power is measured in watts. It's great. We have another W. So W stands for work, and the symbol for watts is W. It's great. It's just not confusing at all. So, however, in normal work, energy, power questions, if an object is accelerating or whatever, they'll ask you what the average power of the force is. You can take the work done by the force and divide by the time. That's fairly straightforward. But now sometimes what happens is that our object is moving at constant speed. Now when it's moving at constant speed, the F net is 0. That also means that net work being done is 0. But if a force is being applied to an object, that force or whatever's doing or whatever's applying that force has a certain amount of power. It has to. Okay, otherwise it wouldn't be able to do anything because work is the rate at which energy is transferred. Well, work is energy being transferred. So what happens here is that if we're now looking at an object moving at constant velocity, okay, it means that the applied force and the frictional forces are all constant, nothing's changing, okay, and it means that we can use this equation where average power is the applied force times the average velocity. And we're using average velocity, but really it means constant, okay, it's the constant velocity. Very, very, very important here, grade 12. So this equation, P equals FV, only applies when you have constant velocity, constant speed, okay? Otherwise, you can't use it. Otherwise, it doesn't work. Then you have to use W over T, okay? So let's look at the equation. And this is very typical. Your CAPS document states that one of the things they're going to look at with power is the bringing up of water through wells, through dams, and the engines needed to bring it up. I'm not really sure why, but it's probably because that's the sort of thing that's quite relevant to us as a country. All right, so now they tell you a windmill is used on a farm to pump water out of a well that is 37 meters deep. The water flows past point A, 37 meters above the well, to the dam with a constant velocity of 2 meters per second. So they've given you a height and they've given you a velocity. Okay, now here we've got a whole bunch of questions that we're going to do, which has to do with energy, work, some nice opinion questions, which are great. All right, so what we're going to do is, there's the question. Hopefully you've taken note of what you need. I'm going to give you 3 minutes, okay, and we're going to see how far you get. So your 3 minutes, grade 12s, starts now. Okay, so grade 12s. Here we go. Nice question. And I'm pretty sure you went, don't even know where to start with question 1. It's all right. Don't stress. It says, calculate, well, let's just go back to the picture. So we know what our picture is. We've got 37 meters. Velocity is 2 meters per second. And the first question was, calculate how much energy is necessary to pump 90 kilograms of water out of the well to point A. Now, we have to pump the water out, which means we have to apply an external force to the water to get it to come up, okay? The next thing that's important here is that it goes at constant velocity. So we know there's a change in velocity, but there's also a change in height. What you also need to recognize is that the initial velocity of the water at the bottom is going to be 0. It can't be moving at 2 meters per second when it's here at the bottom of the well, over here. There's the water. It's sitting there. Once it gets into the pump, then it's going at 2. So we now know that we have a change in velocity, which is actually quite important. Once it starts moving up, it's going at a constant velocity of 2, okay? So there's a change in velocity and there's a change in height, because obviously at the bottom, its height is 0. At the top, its height is 37. So there's both a change in kinetic and there's a change in potential, because there's an external force acting on the water. That is a non-conservative force, okay? Why is that important? Because work and energy are almost interchangeable. Not completely. Work means we use up energy. Energy is defined as the ability to do work. So when we do work, we use energy. When we have energy, we can do a certain amount of work. Their values are the same. So when I'm asking you to calculate how much energy is necessary, I actually want to know how much work needs to be done by the non-conservative force, by the pump. Okay? So work done by the non-conservative force is change in kinetic plus change in potential. So we go, fine, I don't need to know what the force of the pump was, that's irrelevant. So what we're going to do here is change in kinetic means we have to take final minus initial. Okay, guys, your subscripts here are very important. Plus, and I'm putting in brackets because of the minus, it makes the maths a little bit easier for me. Final minus initial. In fact, when I write smaller, I write neater, which is always a good thing for you guys. So, all right, so we have a half, and it was 90 kilograms of water. Final velocity was 2. Initial velocity, I said to you, was 0, so I don't need to substitute it in. I can just put a 0 in there. I don't need to calculate that. Final, well, the mass is 90. Gravity is 9,8. The final height was 37 meters. Initial height was 0. So it has 0 potential. And I also know it's a non-conservative force because my water is gaining both kinetic and potential energy. Okay, and it's getting it through the pump. So what's happening there is we have energy from the pump. However the pump gets its energy, through wind, through rotational, through chemical, whatever, we don't care where it starts. The point is the energy that the pump has now becomes energy for the water, okay, and it turns into mechanical energy. So we now go a half, 90 times 2 squared, plus 90 times 9,8 times 37, which I've already worked out, which is 32,814 joules. That's a lot of energy, but 90 kilograms of water is a lot of water, okay, for this. And to come up 37 meters, that's quite a height. Guys, please remember, 90 kilograms of water would be 90 liters. Okay, water's great, and that 1 liter of water is 1 kilogram. It actually makes it, it's a nice conversion because of its density. So, next question. Now they ask you, all right, so we're back here, and they say to us, is it necessary Oh, I think I've missed something out here because it says, it's a good thing I can read. Apparently we're having one of those. It is necessary, read slowly, to pump 90 kilograms of water per minute. What is the maximum power that the windmill must produce? Now we know how much energy is needed to pump 90 kilograms. Now we put in a time to it. So I'm not just saying now I want the 90 because the energy could take 3 minutes, 2 minutes, 20 minutes, 3 hours, okay? But we've put a time limit to it. So we know how much work needs to get done. That's the work done by the non-conservative force that we've just worked out. That's the energy, okay? So that's the energy we need to expend. The time limit is 1 minute. Big, 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 in capital letters, NB. Very, very important. We never measure time in minutes, ever, for anything. 1 minute means 60 seconds. Please be careful. It's such an easy one to do where you get 1 minute. Okay, so I'm going to go 3,280, 32,814. Really can't read today. And divide by 1. There we go. Off we're happy. No, 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 no. Got to divide by 60. So what does this mean for us? Power equals work divided by time. Okay? That means we're going to go 32,808. There we go. 114 divided by 60. And we get 546,9 watts. Watts means joules per second. Okay? Watts means joules per second. Okay? 500. That's still not actually that powerful at all. In terms of a windmill, 90 kilograms per minute, it's not actually that powerful, but it's a windmill. That means it's dependent on air. Okay? So, from here, they now ask you, now there's a couple extra things they add to, and here it's about reading the question. Because now they say it to you wrong way. Okay, I think I've left something out. Okay, here it is. So now it says to you, the farmer wants to modernize the farm. The farmer decides to buy a 0.5 kilowatt petrol pump. Will the petrol water pump be able to produce the required power? Yes or no? This is important. 0.5 kilowatts. You've got to compare it to an answer which you just worked out that your pump was producing. Let's see, we said it was 546,9 watts. Okay? This is in kilowatts. You can't compare kilowatts and watts. So you need to change the kilowatts into watts or the other way around. I would go kilowatts into watts. That means you times by 1,000. So the petrol pump has only got a power of 500 watts. So, question is, will the petrol pump be able to produce the required power? The answer is no. It's too small. Then the question is, would you advise the farmer to rather use a windmill instead of a petrol water pump? This was only worth one question, 1 mark in the exam. And it depends on whether they ask you to explain a question like this, because of course, this is an opinion-based question. Without an explanation, it's actually very difficult to say whether either question is right or wrong, because some of you will be going, well, in light of what we've just done, that the petrol pump was 500 and the windmill was 546, I would say use the windmill, okay? Because the windmill pump is more powerful, it's one thing, but the other option here is that the windmill pump is actually more environmentally friendly and probably cheaper to run. So the windmill has a lot of advantages. Some of you might be going, no, I would say use petrol. And if I had to ask you why, you could tell me things like, well, petrol's more reliable because the windmill requires wind, and what if there isn't any wind? or you live in Joburg, where we don't get, I mean, we get wind, but it's not as regular as some like Cape Town or Port Elizabeth, okay? And you would also, with a petrol pump, it actually says, why would you advise the farmer? I'll read the question again. Why would you advise the farmer to rather use a windmill instead of a petrol pump? Well, not what you would. It's a good thing I'm reading the question, okay? But I'm just giving you other options. The petrol pump, if you had to say, would you do the windmill or the petrol pump is actually more reliable, okay? Plus, you know what? You buy a bigger petrol pump, hey, you can get more power, you can use it less often, whatever the case may be. But this question was, why would you advise the farmer to use a windmill? It's more environmentally friendly. Brilliant answer, okay? Because we all know we're in for an environmental crisis eventually. And two, it actually has the required power. So it's more powerful than the petrol pump, okay? So it'll do the work necessary. And that's really, really important, okay? So, grade 12s. With this section, I've split it up over the last 2 weeks into 2 different sections. So we looked at conservative, non-conservative, and then we looked at conservative. We looked at conservative last week. We looked at non-conservative this week. Guys, remember they can be asked together. So that's really important. You have to understand this whole section works together. And one more thing, they can put momentum into these sections. So they can add a collision into it. You need to go and find questions where there were collisions as well as the energy. Because we can have a collision and then something happens to the energy as it goes off, like a cart going down a roller coaster and then it collides with something at the bottom which goes off, or whatever the case may be. So please be careful with this one, okay? Learn your definitions, learn your terminology. Those are your easy ones, especially the work energy theorem grade 12s, okay? And practice, 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 okay? So my time is up. I have to now stop talking, which is also very sad, but that's okay. So practice grade 12s, and I will see you again next time.